So you would be surprised by this kind of question at this point. Then I shall talk about an approach which is not usually used by chemists. It is known as the particle approach. In fact, again, in my opinion, it is one of the most beautiful things. And we'll discuss its connection with the random walk. So this is an outline of the first 3 or maybe 4 objectives. So what about two-slit experiments? Well, to do a two-slit experiment, well, you see, what we will do is we will imagine that the two-slit experiment is done. First, we will imagine that it is done with the particles. Okay, and I'm sure all of you will agree that bullets are particles. We have absolutely no doubt that bullets are particles. So I shall imagine, of course, this is a hypothetical experiment. Nobody who is in the right sense will ever do this experiment. And without doing the experiment, you know exactly what is going to happen. Okay, then so we will imagine that this is first done with particles, and then we will think of what happens if the same experiment is done with slits. Then, of course, I mean, you have to do the experiment to get the results, and then finally we will ask what will happen if you do this experiment with electrons or other microscopic things, and the answers are very interesting. So let us imagine that we are going to do this experiment with particles, in fact, bullets. If you want to do a two-slit experiment with the bullets, then obviously you have to have a source of particles, which in this case, of course, would be a gun. So imagine that you have a person who is having a gun, and there are 2 slits. Here are the 2 slits, and this person who is carrying the gun, he is going to shoot out bullets. Just to make things interesting, you can imagine that he is drunk, so he is going to shoot out bullets in random directions. And you have these 2 slits, so what is going to happen is that only some of the bullets will be passing through the 2 slits. And whenever a bullet passes through a slit, what is going to happen? It is going to be incident upon this wall here, which I am going to refer to as the backstop. And whenever a bullet hits the backstop, it is going to leave a mark on this backstop. And as I said, this is an imaginary experiment or a thought experiment, rather to say. And so therefore, because it is a thought experiment, I can imagine that he is given maybe 100,000 bullets, he shoots out all of them. Maybe 5,000 of them will pass through these 2 slits and will be hitting the backstop. And so after he has done this, what will I do? As a scientist, I will go and look at the marks that have been made by the bullets at the backstop. And plot a graph. That's what scientists would normally do, and plot a graph which shows how these marks are distributed on the backstop. And I shall refer to this as an intensity distribution for the bullets. Okay. So if you did that, what would be the result? Okay, there he is shooting out the bullets. And in fact, this figure is taken from that particular website. So here is a schematic arrangement of the results that you will obtain. There are these 2 slits. And I'm going to imagine that only this slit, that is slit number 1, is kept open, while the other slit is kept closed. And so what is going to happen is that any bullet that reaches the backstop would have passed through slit number 1. And most of them, what is going to happen is that they will arrive somewhere in this location, somewhere in the vicinity of that point. But it is also possible that a bullet might hit an edge at this location and be deflected, and perhaps once in a while a bullet may arrive at that location also because of deflections. So as you plot the intensity, what are you going to get? You will get a curve which has a maximum like the one that is shown in the figure, and as you go away from the maximum, the intensity will decrease. And I am going to refer to this intensity distribution as I1. Why the subscript 1? Because I am keeping only slit number 1 open. So suppose instead of doing this, I had kept only slit number 2 open. What would be the result? This curve drawn with the red color would be the result. And I have called it I2. Okay. Now suppose you were to do an experiment where both the slits are kept open. What is the result? I mean, you don't have to actually do this experiment to say what the result will be. At any point, bullets will be arriving. They might have passed through slit number 1 or they might have passed through slit number 2. If they pass through slit number 1, the intensity distribution is I1, while if they pass through slit number 2, intensity distribution is I2. So I12, right? The intensity distribution in the case where both the slits are open, I denote it by the symbol I12. And if I wanted to calculate it, what should I do? I would have to take the sum of I1 and so I12 obviously will be the sum of I1 and I2, and that is simple and straightforward. And not only that, you see, the bullets have another very interesting characteristic. You see, I will always be getting one bullet, or 2 bullets, or 3 bullets, 4 bullets, and so on. I don't ever get fraction. Don't get fraction. So, see, the bullets have something which may be referred to as lumpiness. Right? If I am doing an experiment, I would have 100 bullets, or the next possible number of bullets is only 102. I don't have 101.5. I would have 100 bullets and 101, then 102, 103, and so on. So bullets are what I may refer to as lumpiness, that is a characteristic of particles. Okay. Now suppose I did.
Now let me pause it for some time and okay. Yeah, can you hear me?
Yes, sir.
Yes, sir.
Yeah. Yeah. So we have played the video for some times, and so far Professor Sebastian has discussed what is known as two-slit experiments with bullets. Okay, bullets are particles, huh? So any problem in understanding so far? Anyone has a question? Anyone has a question? So the idea is relatively simple. You have 2 slits and then you're firing a bullet, and these bullets can go either through slit number 1 or through slit number 2. So somebody cannot hear me, but I think that is his problem. Can everyone others can hear?
Yes, sir. Yes.
Yeah.
Yes, sir, we can hear.
Yeah. So,
Raushida, I just wanted to add one thing.
yes. Sure.
So basically, in my lecture notes,
Yeah.
so basically, I usually start with double slit experiment.
Yes.
So it is written pretty detailed.
Yes.
Okay. The entire first lecture note I devoted on double slit experiment. So it is entirely there. So if somebody wants to go through from there, it's okay.
Yes.
Yeah, it's pretty detailed over there.
Yeah. Thank you.
Yeah.
So you guys can go through from the notes. Okay. It's okay. Now the point is that you have 2 slits and you're firing a bullet. Now bullet is a particle, isn't it? Bullet is a particle, and in firing it, you don't expect this to have any web nature. And on the screen you can get the intensity distribution, which is shown by Professor Sebastian, that you have I1, it goes through slit number 1, you have I2, if it goes through slit number 2, and if you keep both the slits open, then the intensity distribution would be just sum of I1 and I2. So I12 is going to be I1 plus I2, and you can see that it has shown this on his slide. So if I try to draw this, let me try to draw this. Sometime. So I'm now going to present it again. Can you see the PowerPoint?
Yes, sir.
Yes.
You can see now.
Yes, sir.
Okay, so the idea is this double slit experiment. And you have a source here. This is you are doing at the gun. The gun is the source, and then you have one slit here. So if you do with one slit, it can go through like this. You have a project. You can take the intensity on the other side, do something like this. This is like I1. Clear? And then you can do another experiment where you do the experiment with say like this, and this is, and for that you get a distribution like this. This is like I2. Okay, now these are not drawn properly. What I meant like that. So if you have one slit is here, other slit is here, and your source is here, and here you have the screen. So it can go like this, it can go like this. So you have a distribution this side I1, and the other side I2. This is the intensity distribution, which is I1. This is the intensity distribution, which is I2. And the total intensity distribution is going to be I12. If I call it I12, I total is just a sum of these two. But remember, we are doing experiments. We're doing the experiment with an electron. No, we are doing this experiment with a bullet. Okay. So this is the result. I1 plus I2 is the total intensity pattern on the screen. So if I plot this, it will be something like, okay, this is your I1. Any question so far? Please ask if you have a question. Hello? Can you hear me?
Yes, sir.
Yeah, so if you have any question, please ask. So, maybe Rahul, you want to add something so far?
Say that again.
Yeah, you want to add something, or
No, that's okay. That's okay. No, that's
Please.
okay. I mean, just the point we are going to make is that the probability is additive.
Yes.
So the probability is additive simply means that they are uncorrelated events.
Yeah, so it is with bullets, huh?
It's with bullets. So basically, I mean, there is no interference.
Yeah,
in the
we'll talk about
probability,
that.
so
Yeah,
no
yeah.
interference in the probability simply means that they are uncorrelated events.
Yes, 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 yes. Yeah. So there is something which Professor Sebastian pointed out, that there is something like what you call lumpiness associated with with the uh, with the bullet, isn't it? So this is like particle. So these bullets are like particles. Is this clear? Any question so far? So far, we are not doing any experiment with any subatomic objects like atom, molecule, or electron. We are doing experiment with a gun, real bullet. So, for example, Akash Ghosh, are you there?
Yes, sir.
Yeah. So, can you hear me? Are we following what I'm
Yes,
saying?
sir. I'm full. Yes, sir. I'm full.
So far, we have discussed the experiment with bullet
Yes.
particles,
Yes.
two objects, and you see the intensity pattern is just additive.
Yes.
I1 plus I2 is the intensity pattern if you keep both the states open. Okay.
Yes.
So now I'm going to again play the video of Sebastian, and again I will play it for some time, then pause it, and then we will again come back. Okay.
Okay. Okay, sir.
Hello.
Yeah. Any question?
Yes, sir. Sir, I want to ask one thing.
Yes. Yes. Okay. Who is this?
Yeah, this is Somesh here.
Okay. Okay. Yeah, Somesh, tell me.
Sir, since we are not dealing with the particle nature here, I
Yeah,
mean,
we are doing particle
wave
nature.
nature, wave
Why?
nature.
Yeah, not wave nature. This is just the particle. The bullets can deflect. So you have a peak which is just opposite to the state, and then around that peak position there will be distribution, isn't it? So bullet is not going to hit the same point every time. No, you are doing the experiment for 1,000 times or 10,000 times. Okay, 1,000,000 times.
So my question was, since we are not dealing with the wave nature, so for particle nature, how we gonna calculate the probability thing? Sir told us na that this is the probability.
No, probability means here the intensity. So basically, what you can calculate if you have a screen. On the screen, the bullet is making some mark. So there will be like dots on number of dots, and you see that at around some point the intensity of dots is very large, and as you go away from that point, the intensity of dots go down. So that's why you have an intensity pattern. You understand? This is where you have the maxima, and then if you go to any other direction, your intensity goes down. So intensity essentially is the number of points, the density, the number of point density, number of points per
It is
unit.
a number of points where the bullet has been hitted.
Yes, yes, yes. If you have a screen, you just calculate the number of points, and you see that there will be a small region where these points are overlapping with each other, and as you go away, you see this point density is less. So from there, you can calculate the intensity. Intensity does not need to be only with wave. Okay. Essentially, you are doing experiments. So it is like I don't know whether you know. This is like constructing what is known as
Interference.
no interference here. No interference here. The interference is truly between the waves. So essentially, it is you are constructing a graph. It's constructing a graph. So we'll talk about it later. But let me play the video of Professor Sebastian. So,
and what is the result? Well, if you
okay, I'll just go back.
it is vibrating.
Yeah.
It's something that goes up and down on the 100 bullet 1. Why the subscript 1? Because I'm keeping right.
Okay.
The intensity distribution in the case where both the slits are open, I denote it by the symbol I12, And if I wanted to calculate it, what should I do? I would have to take the sum of I1 and so I12 obviously will be the sum of I1 and I2, and that is simple and straightforward. And not only that, you see, the bullets have another very interesting characteristic. You see, I will always be getting one bullet, or two bullets, or three bullets, four bullets, and so on. I don't ever get fraction. I don't get fraction. So, see, the bullets have something which may be referred to as lumpiness. Right? If I am doing an experiment, I would have 100 bullets, or the next possible number of bullets is only 102. I don't have 101.5. I would have 100 bullets and 101, then 102, 103, and so on. So bullets are what I may refer to as lumpiness, that is a characteristic of particles. Okay. Now suppose I did the same kind of experiment with waves. This experiment one can actually perform. How to perform it? You can imagine that you have a large cup of water here, and I will have something that is vibrating. Something that goes up and down on the surface of water, maybe a pencil or something. That's an electromechanical device. The device causes the pencil to vibrate, and as it vibrates, it will penetrate and it cuts the surface of water. So that is my source of waves. And then here I will have a wall which will cut the surface of water, or a board or something which will cut the surface of water. And on that, I am going to have slates, so that the waves that I have produced there can pass through these two slates and be detected on the other side. That is the experimental arrangement that you have to imagine. And what is the result? Well, if you schematically represent it, you see you have the two slates, 1 and 2. If I kept only slit number 1 open, what is going to happen? You will get an intensity distribution which may be represented by this green curve called by the name I1. And if you kept only slit number 2 open, what do you get? You will get this curve, red one, denoted by the symbol I2. And the question is, what will happen if you keep both the slits open? In the case of bullets, it was clear that you can get I12 as the sum of I1 and I2, and is that what you are going to get? Well, this is not the result if you are going to do the experiment with waves. The result that you get is not this. You cannot get I12 by adding up I1 with I2, and the actual intensity distribution that you get has a series of maxima and minima. In fact, there are points, for example, a point here or a point there where the intensity is extremely low, close to 0. But there are also points here or there, perhaps, where the intensity is somewhat large. So get a series of maxima and minima, and I'm sure you know the reason for this. This is essentially because waves exhibit the phenomenon of interference. Waves exhibit the phenomenon of interference, and that is the reason why this happens. I shall explain this in a little bit more detail. So it is obvious that if I wanted I12, I cannot get it by adding up I1 with I2. And the question is, how will I get I12? If I wanted to calculate I12, what is the thing that I should do? Well, let us imagine that I have only one slit open. And in such a situation, what is the result? Well, I have kept only one slit open, and you can see that the waves are coming out. The waves are coming out through this slit, and they are spreading. And suppose I am sitting here and trying to look at the waves, then I will find that there is some intensity for those waves at that point. And if I wanted to calculate the intensity, I mean, I'm not going to go into the details of wave physics, but if I wanted to calculate the intensity roughly, you can say, well, the intensity is actually dependent upon the displacement of the water surface at that point. But displacement, as you know, can be in the upward or in the downward direction. So what would you expect? You would expect that the intensity has to be dependent upon square of the displacement. It has to depend upon the square of the displacement of the water surface at that point. As I said, I am not going to giving you all the details, but roughly speaking, it has to be proportional to the it has to depend upon the displacement square. It has to be a quadratic involving displacement. So therefore, you see, if I have only slit number of 1 open, what should I do? At any particular point, maybe a point here, what I will have to do is I will have to look at the displacement and I will have to think of calculating the intensity using the square of something that is quadratic in the displacement. And that displacement, I'm going to denote the displacement. Naturally, you would expect that it should be called a d. I'm going to give a notation, but just for the sake of convenience, I'm going to call it psi. So simply psi. Eventually, psi is going to come into our discussions. So therefore, what will happen is that I will say, okay, I1. Why should I put the subscript I1? Because only slit number 1 is open. And if I wanted to calculate the value of I1, what should I do? I will have to find the displacement at any particular point and take its square, calculate its square essentially. I mean, do something with the psi square essentially. I shall get the intensity. As I said, this is not the complete description, but this is enough for our purpose. Suppose instead of keeping only slit number 1 open, suppose you had kept slit number 2 open. What will be the result? Well, all that will happen is that in particular point, there will be a displacement caused by the waves which are passed through the slit. And that displacement, I am going to call it psi 2. And naturally, the intensity I2 will be dependent upon psi 2 square. Okay. And now suppose I keep both the slits open, right? What is going to happen? Well, if you kept both the slits open, this is how the displacement would be. If you plotted the displacement as a function of position, this is how it is going to be. You can see that, for example, somewhere here there is hardly any displacement. While somewhere there you will see that there is large displacement. Right? Why is it so? The answer is actually extremely simple. I have kept both the slits open. The waves can pass through both the slits. And at any point, what is happening is that there are waves which are passed through slit number 1 and arriving there. There are also waves which are passed through slit number 2 and arriving there. And the net displacement at this location will be due to these two waves. And the displacement due to the first one is psi 1. Displacement due to the second one, let us say it is psi 2. Then what will be the total displacement? Total displacement has to be the sum of these two. So therefore, we have this equation which says that psi 1, 2 must be the sum of psi 1 and psi 2. And what can happen is that you see psi 1 and psi 2 may both be in the positive direction, in which case you will have a large displacement. While it may happen that psi 1 and psi 2 may be having opposite signs, in which case they will cancel each other and you will have very small displacement. That is the reason why you find that you see in this region, there are in this region or in that region there is hardly any displacement, while in this region there is a fairly large displacement. And therefore what will happen if you look at the intensity as you know is going to be calculated as, or it will depend upon the square of psi. So naturally, if psi has a small value, intensity also would have a small value, and that explains how you get this particular interference pattern that we saw earlier. So this is the pattern that you will get. Now suppose you did exactly the same experiment with electrons. So how will you do the experiment? You will imagine that you have an electron gun. So the electron gun is going to shoot to give you electrons. What you will have to do is, I'm not going to go into the details of the experiment, but you will have to select electrons, all of which have the same energy, and pass them through an arrangement of two slits, and you will have to detect where they are arriving on a screen. These things can be done these days. There is no problem with that. The only thing is that you see you cannot do it in this room because this room has air. If I produce an electron, the electron will not go anywhere. It will collide with the molecules and will go somewhere. So you have to do this experiment in ultra high vacuum. And not only that, these days you see you have detectors which are extremely sensitive. They can detect even the arrival of a single electron. Okay. So such an experiment was in fact done. I will give you the details of the experiment in a few minutes. So what you do is you say that okay, this is my source of electrons. These are the two slits, and this is the screen on which I detect the arrival of electrons. If I kept only slit number 1 open, I will get this intensity distribution, which I shall refer to as I1. Well, if I kept only slit number 2 open, you will get I2. And in fact, as I told you, it is possible to detect the arrival of electrons one by one if you want. You can actually see where they are arriving, as you will see in the video which I am going to show you. And you find that electrons actually arrive in lumps. You don't get half an electron, you get 1 electron, 2 electrons, 3 electrons, 4 electrons, and so on. Therefore, in that sense, electrons actually resemble bullets, and bullets are particles. Right? So they seem to be similar to bullets, and therefore, if I use that and ask the question, what will be I12? I12 is the intensity distribution in the case where I keep both the slits open. What would be the expression for I12? And what would be the answer? Obviously, it has to be the sum of I1 and I2. It has to be. So the expectation is that I12 must be the sum of I1 and I2. But if you actually do the experiment, you don't get the result to be this sum. But what you get is actually an interference pattern. So even though electrons are like bullets, in that they arrive in lumps, the intensity distribution that you experimentally find is not characteristic of particles, but it is characteristic of waves which exhibit interference phenomena. Okay. So in this case, I1 plus I2 is not equal to I12. But suppose I wanted to calculate I12, what should I do? Well, it means that you see, just like we thought of the wave function, so to say, the wave function in the case of water waves, what was it? It was actually the displacement of the water surface. Just like that, you have to imagine there is something that is associated with the electron, which we will refer to as the wave function and called by the symbol or denote by the symbol psi. What is the use of it? Well, the use is that from it we can calculate the intensity. Okay. Number of electrons arriving at a particular location. I can calculate from this psi, and it so happens that in the case of electrons, all that you need is you take the wave function, the psi, and take its square, you will get something that is proportional to the density. So that is something that you will have to assume. In fact, instead of saying that it is proportional, I have just said that it is equal to, but strictly speaking, it is proportional. Okay. So I12 is the intensity of electrons arriving at different locations on my. When I say intensity of electrons, it essentially means number of electrons arriving per unit. So I12 we can calculate from a knowledge of the wave function, and it will be, well, strictly, as I said, strictly speaking, there will be a proportionality constant also, but for the sake of simplifying the notation, I have omitted that. So I12 is actually equal to psi12 square. But if you wanted to calculate psi12, what will you do? Just as in the previous case, what you will have to do is you will have to say that psi12 has to have two contributions, one coming from things that are passed through slit number 1, and the other coming from things or waves which are passed through slit number 2, and therefore psi12 must be the sum of psi1 and psi2. So what is I1? We will say that it is contribution to the wave function of the electron from the waves which have passed through bit number 1. And Psi2 again, similar thing, contribution from the waves which have passed through bit number 2. And these two contributions I have to add together. I am going to get the total wave function. And once I get the total wave function, what should I do? I should take its magnitude and square it. I am going to get the intensity. Okay. This is the address where you should have a look at, and the experiment that was carried out by these people is the one that is shown in this picture. They have a source of electrons which produce mono-energetic electrons. That means electrons out of the same energy, and they had a very thin wire. Here is the wire. It is only 1/1000 of a millimeter thick, and the electrons from the source can pass through the left side of the wire or through the right side of the wire. So essentially, this is our slit, and they are incident upon a detector. This detector is actually capable of detecting the arrival of a single electron. This was essentially developed by the Hitachi company, and so the experiment was carried out in the Hitachi company in Japan. So what I'm going to show you is a video taken from their website. And what you are going to see is the thing that is seen on the screen. On the screen, you will find that bright spots appear. These bright spots, each one of them is a single electron arriving at the screen. Okay.
So we'll take a pause here. So the whole thing is, can you hear me? Can you hear me?
Yes, sir.
Yeah. So the whole thing is, if you do an experiment with a bullet and then you do the same experiment with water wave, you see a difference. These bullets have what is known as lumpiness, the particle nature, the particles. But with water, you get to see something else. So with water, what you see is already explained by Professor Sebastian. So you have any query or any question, please ask me. Any questions so far?
Hello, sir.
Yes.
Sir, why it is necessary to have all the electrons of the same energy? What will be the problem if they are not of the same energy?
So I can always have electron in the same energy, or okay, yeah. If they are not of same energy, I don't see much problem. But what I can see that if they are of different energy, then the intensity pattern. Maybe Rahul, can you tell me? You have an answer to this question? Better answer.
Yeah, I think that it's more about the intensity because that's directly related to your energy.
Yes, so I would say that you need to have some control over the intensity. It should not be such that you cannot have a control.
You simply don't get a symmetric pattern.
Yes, because you have some electrons which are of high energy and some electrons which are of very low energy. So yeah, so better to in order to have a clean experiment, I think you should have electrons which are of same energy. So that is how qualitatively that is the answer.
Okay,
So,
thank you, sir.
But any other queries? Any other queries?
Sir, if you have a very fine microscope, then can we observe the interference pattern for the case of bullets? I mean,
bullets, I don't think so, because in principle, bullets should also have wave property. But
yeah. on a very fine scale, right? And
I
that
mean,
that leads to average.
in principle you can, but the resolution that is needed to construct
Yeah.
that kind of a microscope,
Yeah. That is
that
is
you will
very
see that
difficult.
it will
Yeah.
in principle violate uncertainty principle.
Yeah. Exactly. Yeah.
So I did not want to answer this question because we have not introduced this uncertainty principle. So it is related to that. The whole thing is that with bullet, actually, in principle, you should be able to do experiments with elephants also. But in reality, you cannot see the elephants interfering, isn't it? Like every object on Earth, like everything has a wave property, but that only if the particles are small, subatomic, then only these wave properties can be considered.
Detectable. Yeah.
Yeah. Otherwise, detectable, and otherwise it is just negligible. This quantum effects. We have not discussed that, so I don't want to discuss it now. So, but so far the idea is that if you do the experiment with waves such as water wave, they interfere, and that you have seen. So you have state 1 and state 2, and then your source of wave, because it's something is creating this disturbance in water and creates a water wave which will propagate and go through state 1. You have one intensity pattern, then it will go to state 2 in the second experiment, and then you do another experiment where you keep both the states open, and then you see the intensity pattern. And strangely, you see that it is not the lumpiness. It is intensity is not just addition of total intensity is just not the addition of I1 and I2. It is something more. There are places where the intensity is low, and there are places where the intensity is high. The intensity shows some kind of oscillations. Okay. And I think Professor Sebastian already had shown the intensity pattern for this case, for water. And you do the now same experiment with something like electrons. We have a source which will generate electron, it passes through the rod, you see, and then it creates the intensity pattern. It's done in the Hitachi company in Japan. You see the video now, you'll see. And you'll see similar intensity pattern as you see with water, which basically tells you that the electrons, which you usually, to begin with, you'll assume these are particles. They are not really only particles. They are particle at the same time they are wave. So there is something like a wave nature associated with electrons, which one would like to think it as a particle. So it essentially tells you that electron is not only a particle; it also has wave nature. So what I'm now going to do, I'm now going to play the video. The video means the video from Sebastian.
Rashida, if I can just add one sentence. If I just can add one sentence, that is, you will see that it possesses also the particle nature. It has some sort of a lumpiness as well.
Yeah.
So electron has particle natures, but its pattern or the probability is distributed just like a wave.
Yeah, yes, it's particle as well as
It's a particle wave in that sense. It has the lumpiness, but the distribution pattern is like a wave.
Yes.
Sir, sir,
Yeah,
sir, can I ask something? So, since electron carries the dual nature, right, wave plus particle. So here we are getting the wave nature, the interference pattern. So is there any way that we will get only the particle pattern for electrons? Like the bullets, the one we got for bullets.
If you try to measure this experiment or if you try to perform a measurement, you will see either a wave or particle nature.
So basically, if we observe it, right, sir, the law of Copenhagen, like if we try to observe it, we will get any one, like either the particle or the wave.
Precisely, yeah.
Yes, sir. Okay, sir, got it.
Yeah, if you try to observe it, so it's basically collapses to one of the states.
Yes, sir, got it. Yes, thank you so much.
Yeah, so we'll discuss that later. So the whole thing is that they are wave as well as electron, particle. And depending on the experiment you design, or depending on the experiment you design, you can see the particle nature as well as or the wave nature. So we'll discuss that later, okay? Because I just want to introduce this wave particle duality fast, and then we'll discuss. So let me play the video.
Now we are looking at the detector plane on the monitor. Bright spots appear here and there. These spots indicate individual electrons. Electrons are sent out only occasionally. Therefore, the chance of finding one electron in the microscope is very small, not to mention the chance of finding two. Since electrons are detected one by one as particles, we have to conclude that each electron must have passed through at random on either side of the biboson, thus creating a uniform distribution without any interference when accumulated. Under such conditions do electrons form a uniform distribution. But look, we begin to see some fringes in the perpendicular direction that looks like interference fringes. Since this experiment lasted for more than 30 minutes, I have sped the movie up. Interference fringes are now clearly visible.
Therefore, you have seen the video and you can see that this is data from an actual experiment. The interference patterns are clearly visible, and this indicates that electrons do have a wave associated with them. Also, it has shown you that electrons arrive one by one and therefore they resemble bullets, and so they have to be referred to as particles. But these are particles which also have a wave nature. Okay, this is the actual paper in which this data was published. It's of great interest to anybody who is interested in physics, particularly quantum physics.
So I can share the paper, okay, if you want, but it is too difficult for, I think, most of you to read. Can you hear me? Can you hear me?
Yes,
Rahul?
Yes, yes, I can. I can.
Yeah, so that paper I can share, but this is going to be quite difficult. But as Professor Sebastian pointed out, that when these electrons arrive, they arrive as particles because you have dots on the screen. But when you see the intensity pattern, this is just an intensity pattern of a wave. So they interfere. So they arrive like particles, but on the way they interfere with each other. And that interference is truly wave nature of electron. But making spot on the screen is actually the particle nature of electron. I think this is fine, no? Rahul, I think this is another way of saying the same
Yes,
thing.
it is. Yeah.
Yes. So we'll continue. This is an excellent experiment, as you can see. And this essentially tells you that electrons are behaving like wave as well as particle. This is what is known as wave-particle duality. So let me play the video again.
In fact, somebody had put together a list of 10 most interesting experiments ever carried out in physics. The list was prepared, and I think this is actually either number 1 or number 2 in that list. So this is considered to be among the most interesting experiments carried out by physicists. And that is the exact reference. But then you see, you have to notice something that has happened in the video. See, the electrons were actually sent out from the gun under identical conditions. They were all prepared in the same fashion. They were all coming out of the gun. But then when you look at the video screen, what has happened is that they are arriving at different locations. Right? This seems to violate the basic ideas of doing experiments. You see, if you do an experiment, you would expect that the result will always be the same, and this doesn't seem to be happening in this particular experiment, because if I send out one electron, it may arrive somewhere here at the detector, but the next time the electron is arriving somewhere there. The third time the electron is arriving somewhere else. Right? This is as if suppose you are in the chemistry lab doing a titration. The first time you do the titration, you get an answer of maybe 15. Next time you do the experiment, you get an answer of 22.1. And the third time you get an answer of 30.2. And then you would think that, okay, this is not the way science is. The basic idea of science is that the experiments repeated again and again should give you the same. But here what happens is that when you send out one electron, you cannot say exactly where it is going to be. You can only talk of the probability. See, for example, you had bright regions. And there you can say there is a large probability that the electron will arrive there. You also had darker regions there, you can say, okay, the probability of finding them is small. So here it seems that we can make only probabilistic statements, not exact statements. So then you will ask, in what sense is this particular experiment reproducible? The answer is the following. Suppose you had sent out maybe 100,000 electrons and collected the pattern, then you will get an interference pattern. If somebody else somewhere else in the world does the same experiment with 100,000 electrons and gets the pattern, then your pattern and his pattern will be identical. So therefore the experiment is reproducible only in that sense. But if you are sending out only one electron, you cannot actually say where it is going to arrive. You can only talk of the probability that it will arrive at a particular location. That you can talk about. Okay? And if you wanted to calculate the probability, what is the procedure that you can adopt? The answer is that you have to go back to your wave function. If you actually wanted to find the probability, you will have to calculate or you find the wave function. And you will obviously be able to say that the probability should be proportional to the square of this wave function. Earlier we were saying intensity is proportional to the square of the wave function. We modify that slightly because we are now thinking of a single electron. And if I am sending out a single electron, I can say, okay, my wave function is going to give me something which is proportional to the probability. That is actually psi square. The wave function square will be proportional to the probability of arriving at any particular location. Now, there were great scientists who were very unhappy with this. You see, they thought that if I send out a single electron, it should be possible for me to say exactly where it arrives. But quantum mechanics does not do that. So, scientists like Einstein were very unhappy about it. In fact, Einstein made a very famous statement. He said that, you see, the way the behavior of an electron is described in quantum mechanics is not completely satisfactory because you know that if I had a die and if I toss it, then the answer can be any one of the numbers 1 to 6. And nobody can say a priori what the answer will be. You can only talk of the probability that the answer is a 5 or a 6 or a 4 and so on. And he said, you see, in the case of a single electron, if you are sending out a single electron, you are talking only of the probability that the electron will arrive at different locations, and that cannot be correct. And therefore, he made this very famous statement, which is reproduced here: God does not play the game of dice. By which what he meant was that he does not believe in the description of nature using quantum mechanics. He thought that it was not complete. But whatever experimental evidence we have till today indicates that this universe obeys quantum mechanics, and it seems that God does play the game of dice. And again, historically speaking, this kind of behavior was actually first observed in the case of light. So by this, what I mean is this experiment regarding wave-particle duality or dual nature of microscopic things was first observed in the case of light. So this is a little bit of history, not too much details. This is actually Newton. And he was among the first to propose a theory of light. What he said was that light is a beam of particles. This was his suggestion. Even though before him, Huygens had suggested that light exhibits interference and therefore you have to think of it as waves. But you see, Newton was much more well known than Huygens, and because he was so much more famous, people simply accepted what Newton said and they discarded the wave theory of Huygens. But then later on, what happened was Maxwell came along, he formulated what is known as the electromagnetic theory of light, according to which light has a wave nature. And this was accepted, it could explain so many experimental phenomena, and therefore the theory of Maxwell was accepted. Until Einstein came along, and he said that in order to explain the phenomenon of photoelectric effect, the experimental observations of photoelectric effect, you have to assume that light has a particle nature. So all the external observations regarding like photoelectric effect could be explained assuming that light has a particle nature, it is a beam of particles. But even though Einstein made this suggestion, nobody believed him. The suggestion was made in 1909, so in 1905. And there is this person, Millikan, who won the Nobel Prize. He didn't believe in the suggestions of Einstein and he wanted to disprove them, and therefore he did a series of careful experiments in photoelectric effect. And he surprised found that whatever Einstein had suggested was completely correct. So then came along Compton, and he did scattering experiments in which X-rays were scattered from a piece of metal, and there was a change in the wavelength caused by the scattering, and he could explain this by assuming that scattering process is nothing but the collision, so it is similar to collision between two billiard balls. You can imagine you have the particles of light, which we now refer to as the photons. They collide with the electrons of the metal, something like the collision between two particles. And all the experiments could be explained using a particle picture. But then, of course, it is also known that light exhibits the phenomenon of interference, and therefore it has a wave nature, and therefore scientists were very puzzled. So they were puzzled because you see, it appeared to them, this is only a joke, it appeared to them that on Mondays, Wednesdays, and Fridays, light seemed to behave like a particle, while on Tuesdays, Thursdays, and Saturdays, it seemed to behave like a wave. And actually, that is the way it is. You have the question, what about on Sundays? Well, the scientists of those days, this, as I said, is okay joke, scientists of those days would go to their place of worship and perhaps pray to God as to a clarification whether this is a particle or a wave. But now it is clear to us, actually, it is quite well established that light has a dual nature. Not only light, it appears as if everything in this universe has a dual nature. Right? Even electrons, neutrons, protons, helium atoms, C60, which is a rather big molecule, this also has been demonstrated to have a wave nature. So people have been trying to show this wave nature experimentally. For different particles, they have succeeded for electrons, neutrons, protons, even for bigger systems like C60. But of course, you see, we don't have external evidence for much bigger systems. If somebody says that I have a wave nature, I being a big particle, you can say, okay, I would probably be expected to have a wave nature. There is absolutely no experimental evidence. So we would like to extrapolate and say that even bigger objects have a wave nature. So this is a C60 molecule, a nice football-shaped object, and I want to show you experimental data taken from the group of Anton Zeilinger. His name you will see in a second. So you can see the interference pattern that he found. Okay, you can see this pattern, which is just an interference pattern. And this is obtained using a beam of C60 molecules. He made a beam of monoenergetic C60 molecules, passed them through two slits, and then observed this experiment, this interference pattern, showing that even a C60 molecule has a wave associated with it. Okay, these are pictures taken from his website. You should have a look at his website. His address is given. Okay. Now, though, a few words about these two pictures. Actually, this is again another joke. These two pictures. Suppose you are playing football and imagine that the ball has a wave nature, what will happen? Right? I mean, the ball has a wave nature, and let's imagine the wavelength is rather large. Suppose that is not the actual way it is. Then suppose you see I am standing here, I am the body, and one of you is going to stand there, and it is a kick penalty. So therefore, you are going to shoot the ball. Suppose you shoot it directly at me. In our classical world, what will happen is that if you shoot it directly at me, and if I don't move, I mean, obviously it will not be a goal because the ball will hit me and it will go somewhere else. But if the football had a wave nature, what is going to happen is that the wave associated with the football can go through this side of me or through the other side of me, and right exactly at my back, what will happen? It will be constructive interference. Exactly at my back. So therefore, even though I am standing, obstructing it, it can directly go and can be a goal. Right? Of course, this will not happen if you do not have a wave nature associated with the ball, which we don't have in our real world. I mean, the wavelength associated with the football in our real world, we would expect is very small, and therefore you don't see any interference effects. Okay, well, as I said, people have been doing experiments.
Okay, I'll take a break again. From here, like break means pause. So I think he has explained it nicely. And any question? Now I'll take questions. I think that is the best way to do. So anyone has a question? Now Kingshuk Sharkar, are you there?
Yes, sir.
Yeah. So you have any question?
Sir, I was wondering, we are observing the electrons with the help of the clicking made on the sensor. So, I say that we have two sources of electron, one with higher energy and one with lower, will it affect the interference pattern? Because it is not affecting the clicking, because I am still sending the same amount of electrons.
I don't really. I think it is the same question somebody has asked. Look like that whether you can do experiment with electrons with different intensity, different energies. Are you asking the same question?
Yes, sir.
Yeah, I told you it is better to create electron in the same energy state and do the experiment with the electrons in the same energy state. In principle, if you should be able to do the experiment with electrons which are in different energy states, but it's always better to have it in the same energy state so that you have a clean experiment. So you have an intensity pattern which you can explain. Maybe you want to add something, Rahul? Are you there? Rahul, are you there? I think it's left.
Oh, sorry. I was speaking continuously without the microphone on.
Okay.
Can you please pose the question once again?
He is again asking whether you can design an experiment with electron source which will generate electrons with different energies.
So basically, if you two things that you need to take care of. One is basically the intensity of the light, or rather intensity of the electrons. That is the first thing. So I believe that, if you increase the intensity of the electrons, you see some different things. So for example, if you increase or decrease the intensity of the electron and try to measure it, you will see that some of the electrons just pass through the slits without being noticed, and some of the electrons are actually interacts with the photon source to give some flashes here and there, just to see their particle natures. So intensity actually doesn't have that much of effect. Rather, whether you are increasing or decreasing the wavelength of the light, that matters more. So intensity, no. What is the precise question you have?
No, I think you can tell. Okay, tell Inshu, what is your question?
So I was asking that we are observing the electrons on the basis of the clicks it makes on the sensor.
Yeah.
I was saying that if we use two sources, one has an electron with a higher energy and one has an electron with a lower energy, and keeping
instead of having one source, you are making two sources.
Yes, sir. I am making two. I used the coherent source in the experiment shown by the sir used the coherent source. So I am saying if we use two different sources, one has electrons with higher energy,
So,
another
so
has electrons with lower
two
energy.
different sources simultaneously?
Yes, sir.
Okay.
But the number of electrons is still the same as we are seeing here. Say 100 electrons pass
But
through.
Ikshu, let me ask you, why do you want to do that experiment? Will it give you anything new?
So I was wondering that we are observing the electrons on the basis of the clicks it makes on the detector and later on the flashes.
Yeah.
So if I am sending the same number of electrons, the number of clicks will still be the same. So if I vary their energy, will it affect the interference pattern? And if it does, how will it affect and what will be the consequence?
So see the wavelength or the say particle wavelength of your electrons that remain fixed with your being it high intensity or low intensity. It matters whether you are trying to detect it through a low intensity light source in the middle of the two slits or a low intensity light source. That's what it matters.
But Rahul, if you create electrons with two different energies,
Hmm.
then they would have a different wavelength, isn't it?
Yes, that is fine. That is fine.
Yeah. So the interference pattern would be different.
Interference pattern would be different. So if you have a larger wavelength, it has less probability that it will interact with the photon.
I think one answer is that not with two sources. If you create many sources with different energies, so electrons with different wavelength, this is called de Broglie's wavelength, which we'll discuss in the next class. Then they will interfere in such a way that maybe it is possible that you see lot of destructive interference and you see very localized intensity pattern. It is possible that actually you can create an intensity pattern that is very localized.
So basically, it all matters that whether you are going to detect the interference pattern or not is all about whether your electron is actually interacting with the photon. Now, if your electron has a longer wavelength, it is of course not going to. Not all the electrons are going to interact with your photon, and some of will just pass through the slits without being interacting with the photon, or rather without being detected.
Yeah, the electrons are interacting.
Yes, so that's what I'm saying. So basically, in that sense, the electrons which have a longer wavelength, it has much higher probability that it will pass through without being detected, and it will show the interference pattern. While the shorter wavelength ones, that will more or less more frequently interact with the photon and will show a more particle nature.
Photon means where do you get photon here?
Oh, I just wanted to detect. Okay, I can give you another perspective. So you just go ahead right now. So go ahead right now, because I haven't seen exactly what Professor Sebastian was saying in the middle.
No. So there is a photon. They have to experiment with electron, just like with bullets. So electron source is going like this. It's getting going through two slits, whatever the experimental setup. But my question is that if you do the experiment with many electrons, like electrons with different energies, what is going to happen that these electrons, if you use this different
Okay. So you are not interacting with any photon source or anything.
No.
Oh, okay. No, it simply will have a different interference pattern. That's it.
Yes. In principle, should be possible.
Yes. No, I was thinking something else completely, because I haven't heard the entire part what Sebastian had said.
Okay. Yeah.
So I had something else in mind.
Yes. So, but the whole thing is, what is the message is that electrons, they are like particle as well as wave. They have this dual nature.
Yes.
This is called wave-particle duality. And then also he mentioned and showed an experiment done with a big molecule like C60.
Yeah.
You know, C60, a big molecule. I'm asking students. Even with C60, you get to see the interference pattern. So C60 also has this wave nature, along with the particle nature. And then he briefly mentioned and the history of light. It started with Newton and others. So you can say this light got they're like particles, and then Newton said they're like wave, and then much later Einstein used the particle nature of light to explain what is known as photoelectric effect. But later, actually, Einstein also said that he doesn't believe in quantum mechanics, because he is the one who started the old quantum theory by explaining photoelectric effect. And even for that, Einstein got the Nobel Prize for photoelectric effect. So even light has this particle as well as wave nature. Electron has it. So everything rather, on this universe has this dual character, wave particle duality. That's the message. So any other question?
Hello, sir.
Actually, Kingshu will come back and we'll talk about wave packet. We'll talk about electrons with different wavelength. Yeah.
Sir, I have one question.
Okay, Somesh, who is this guy? Okay.
From Samikshan.
Samikshan, yes, tell me.
Sir, I just wanted to confirm that what am I thinking is right or not.
Yes.
That if we are using electrons of the same energy,
yes,
then the wavelengths will also be very similar to them.
Yes, the same wavelength. Yes.
So that is so we can say that constructive interference will be better if the waves are of same wavelength.
See, this will be clear. For example, I'll give you a very simple example. If you take electrons of different energies, they'll have different wavelengths. And if you just when they interfere, so you see that because of these different wavelengths, there is a lot of destructive interference. And it's possible to create a wave packet, which we call wave packet, which is very localized in one.
Yeah, sir, exactly. If we take different wavelengths,
qualitatively is correct. Qualitatively correct. Okay.
So, sir, if we take different wavelengths, then a standing wave will form, right?
So it is related to what is known as Heisenberg uncertainty principle, which we'll discuss in the next class. Okay. Essentially, if you have electrons with same wavelength, it basically means you know the momentum. The wavelength.
I mean, very simply put, you see that for the interference to take place,
yes,
you have to have basically. So, for example, for what happens for bullet? For bullet, if you go over there, so basically you see that the intensity or the probability, which is the measure of the intensity in the case of a particle, that is simply additive. In case of a wave, if you think that the intensity going through slit number 1 is I1 and the intensity going through slit number 2 is I2, then the total intensity that you see in the what is called that this backdrop or whatever, the backstop, whatever it's called, the intensity measured, that is no longer I1 plus I2. It's rather no longer I1 squared plus I2 squared. It's rather modulus of I1 plus I2 entire squared. Okay, so that gives you I1. So I mean not entire squared. So basically, I1 is proportional to the the amplitude of the standing wave.
Yeah.
So basically, now what happens? It is basically the intensity that you observe is I1 plus I2 plus twice I1 I2 cos theta. The theta is the phase difference between two waves.
Yes.
So you see that depending on whether it's I mean cos theta is whether +1 or -1 or some other value, it can have the value is twice I1 plus I2, or something less than that if it's a negative value. So you get a constructive or destructive interference.
It is just like A plus B.
It's just like the waves.
It's just A plus B whole square.
It's just A plus B whole square, just with a phase factor.
Yes.
Phase factor comes from because the two waves might have a different phase. Now the question is that this intensity, which is basically a measure of the height squared, the height is the height of the wave front. That is basically the measure of so that is the amplitude, right? The intensity. And you know that this intensity is inversely proportional to the wavelength. Yeah. And intensity is directly proportional to the energy.
Yes.
And that's it.
Yeah, we'll talk about it later because as time progresses, I think this will be clearer. And I don't think I'm going to play the rest of the video because you guys can go and watch the video of Professor Sebastian. So today's conclusion is that electron, light, or anything on this universe has dual nature, wave and particle. And then the next class will introduce what is known as wave particle duality mathematically using a hypothesis by de Broglie. It is called de Broglie's hypothesis. And we'll talk about what is known as Heisenberg's uncertainty principle, and that is the most important thing in quantum mechanics. Okay. So how many of you heard about Heisenberg uncertainty principle? How many?
Yes, sir.
So Pooja, tell me, what do you know about Heisenberg's? Pooja, what do you know? Pooja, you can tell me. Where is Pooja? So anyone else? Anyone else wants to tell me what is Heisenberg's uncertainty principle? Qualitatively,
Uh,
Akash.
it is impossible to measure simultaneously position and the linear momentum.
Yeah, yeah.
And
Okay. So in the next class, we'll see that there's a relation. Uh, there's a relation between what is known as de Broglie wavelength or with the momentum. So lambda is h over p, h divided by p. H is Planck's constant. So if I know if I have an electron with fixed energy which has a fixed wavelength, I think, then it has a momentum which is very definite. But then what happens that if you have to measure that electron, since it is it has a definite wavelength, it's a definite momentum. But because of this Heisenberg's uncertainty principle, the position of that electron would be very, very uncertain. And you can do the other way. You can create something like known as localized wave packet, where you superimpose many electrons, or many waves rather, with different wavelengths, lambda 1, lambda 2, lambda 3. So essentially with different momenta, P1, P2, P3. Then it is localized in space. The uncertainty in position or x is very, very small. But since you have overlap waves of different wavelengths or different momenta, you have very much uncertain momentum information. So the momentum is very, very uncertain. Position is more or less certain. Because there is nothing called free lunch. You cannot simultaneously measure momentum and the position. With certainty. There is always some inherent uncertainty associated with your measurement, and it cannot be overcome by any sophisticated experiment. This is the fundamental. You cannot design an experiment, you cannot perform an experiment. We should actually say this principle is not valid. Okay, so we'll discuss that in the next class. Okay, so from the next class, entries are only with LDAP, and the next class is on Wednesday, 11 o'clock in the morning. But we have enough time. I'm going to send this video today and some other material if possible by today evening. And meanwhile, you can start discussing things on WhatsApp. You have the WhatsApp and you can start discussing. I can join, Rahul can join. You guys can discuss among yourself. Okay. So make use of WhatsApp. So you start discussing things. And I hope you're enjoying this course. But we have only just 2 classes. I'm sure that you're going to enjoy it because they're going to be this course is going to be very interactive. It's not like any other course. I can assure you that. Okay,
I just wanted to add one thing, Rajushida.
Yeah.
Is that I don't know whether Professor Sebastian is going to introduce the uncertainty principle from which perspective, but in the lecture note that I prepared, you see that from the double slit experiment itself,
yes,
the Heisenberg's uncertainty principle has been derived. Not derived, but intuitively stated.
Yeah.
We'll
talk about it in the next class.
We'll talk about that. So you also go through that lecture note.
Yeah. We are going to make a hybrid.
Yeah.
Okay, so combination of your note and Professor Sebastian lecture.
Yeah, that's what everything, and then the discussion.
And putting everything together because you have to have a overall understanding.
Yeah.
Understanding. Okay, thank you very much. So be safe and healthy, and I think we can conclude today, and we can start discussing over WhatsApp. Thank you very much.